All right. So, first of all, the next example is one that's actually in the textbook. And usually I try to avoid doing examples straight out of the textbook because I want to give you more examples, right? And it's sort of redundant. But for this particular type of problem, which is the infinity minus infinity indeterminate form, this is kind of difficult to find examples of. There aren't very many. It's just hard. I can't just pull them out of nowhere. Like for some examples, for some types of problems, it's easy to come up with them on the fly. But these are a little harder. So I decided to go ahead and do the one that's in the textbook. So I'll walk through it with you, and you can read it in the textbook for an alternate take on this problem. So first of all, here's the function. It's the limit as x approaches 1 from the right of 1 over the natural log of x minus 1 over x minus 1. The fact that we're approaching 1 from the right is going to turn out to be important. Let's first of all figure out what are the limits of each of these terms individually. Turns out it's going to be infinity minus infinity, but let's figure that out. Pretend you didn't know that yet. Let's just take the limit as x approaches 1 from the right of 1 over the natural log of x. Well, if we think of the natural log of x as being u, let's have u equal natural log of x. The graph of that is going to be this function, right? And as x approaches 1, 1 is right here, right? Right where it has its x-intercept. And so as x approaches 1 from the right, then we're going to be talking about points coming in from the function on the curve this direction, which means y is going to be approaching 0 from above. So what we get here is this is the same as the limit as u approaches 0 from the right, because this is coming down from above, from the positive side, of 1 over u. And that's replacing, since u equals natural log of x, we're going to replace the natural log of x with the u. So I did this variable conversion, okay? Figured out what the limit of the natural log of x is as x approaches 1 from the right, and I just did the graph to explain it. And then this limit is positive infinity. Okay, so that's the first of these two terms is approaching positive infinity. Then let's look at the second one. The limit as x approaches 1 from the right of 1 over x minus 1. Well, again, you can do u equals x minus 1. Let's do a quick graph of x minus 1. It looks like this. And it also crosses the x-axis here at 1 in a very similar manner. So as x approaches 1 from the left, we're talking about coming in along the line like this, which means y is going to be approaching 0, again from the right. So this will be the limit as u approaches 0 from the right of 1 over u again, which is again positive infinity. It's the same thing. So subtract, and then that term is also approaching infinity. So far, this all here is just showing us. I'm just doing the limits of each term individually, and this is just showing us that this is in the form infinity minus infinity. Now, when you have infinity minus infinity, if those two functions are growing towards infinity at the same rate, then that might cancel out completely. Like x minus x, x and x are growing towards infinity at the same rate. So when you subtract them, they all cancel each other out completely and give you 0. That's not always true. If you had x squared minus x, for example, x squared minus x is actually a parabola that curves up and approaches infinity. So even though x squared is approaching infinity and x is approaching infinity, when you subtract them, you don't get 0, right? They don't cancel each other out because the first function was growing towards infinity faster than the second one. So that's why this is indeterminate. Is we don't necessarily know immediately the relative rate at which these functions are approaching infinity, right? When you subtract them, are they going to cancel out, or is one of them going to overpower the other? Maybe the second one is going to be bigger, and it's going to approach 0, or maybe the first one is going to be bigger, and it's going to approach infinity, or maybe they're going to balance and approach some finite value, right? Like any of those things can happen. So what we can do is we can do, as often is the case, we can do a bit of algebra to manipulate this into a format which is a little easier to work with. So in particular, this time, we're going to take these two terms and combine them into one term. So I want to get a denominator, which is a product of these two denominators. So I want my denominator to be the natural log of x times x minus 1. And in order to get that, I need to multiply my first function by x minus 1 over x minus 1. And I need to multiply my second function by the natural log of x over the natural log of x, okay, in order to get a common denominator. So now my numerator is going to be x minus 1 minus 1 times the natural log of x, like that. And this, if you look at x approaching 1, we're going to get 1 minus the natural log of 1. Natural log of 1 equals 0. So if we think about x being 1, we're going to get 0 minus 0. So that's approaching 0 in the numerator. And then in the denominator, we have the natural log of 1, which is 0, times 1 minus 1, which is also 0. So that all is approaching 0 in the denominator. So just this act of combining them into one term instead of two has put it into a format to which we can apply L'Hopital's rule. So let's go ahead and do that right away. We apply L'Hopital to this. We get the limit as x approaches 1 from the right of derivative of the numerator is going to be 1 minus 0, and then minus the derivative of natural log of x, which is 1 over x. Okay? Divided by, we have to use the product rule to take the derivative of the denominator, right? To get the derivative of the denominator, we need the product rule. This is going to be the derivative of the first function, 1 over x, times the second function, x minus 1, and then plus the first function, natural log of x, times the derivative of the second function, which is 1. So there we go. That's our denominator. So that is by L'Hopital's rule, okay? Now, we still have a problem. If x is 1, then you're going to get 1 minus 1 over 1. That's going to be 0. And in the denominator, you're going to get 1 over 1 times 1 minus 1, which is 0, plus the natural log of 1, which is also 0. So this is all still 0 over 0. To try to mitigate this, at least make it simpler, I mean, you could differentiate right now. You could differentiate that again, numerator and denominator. You could do L'Hopital's rule again, but that's going to be pretty messy. So what I want to do is simplify this a little bit before we do another L'Hopital. So let's multiply both the numerator and denominator by x, because that's going to clear away the fractions and give me a simpler function. So that step there is going to give me x minus 1 in the numerator, much easier to work with. I'd rather differentiate that than the rational function there. So that's x minus 1. And then in the denominator, when I distribute, that's going to cancel the 1 over x over here, so I get x minus 1 by itself there. And then plus x times the natural log of x. Okay, so that simplified it a little bit, but it's still 1 minus 1 over 1 minus 1 plus 1 times natural log of 1. Which is 0. So this is still 0 over 0. All right. So we do need to do L'Hopital's rule again, but hopefully now that I have simplified it a little bit, now when we do L'Hopital's rule, hopefully it should be something much easier to work with. So the derivative of the numerator is now 1. That's very promising because it's not a function of x, so it can't be 0 or infinity. Okay, and then in the denominator, we're going to get 1 minus 0 plus, and then we have to get the derivative of x times the natural log of x. That's going to be a product rule right here. So we're going to get the derivative of x is 1 times the natural log of x, and then plus x times the derivative of the natural log, which is 1 over x. So that all is going to end up being natural log of x plus 1. So now, what is this equal to? Whew! The numerator is approaching 1. That's great. And then in the denominator, we can evaluate this limit by direct substitution. So we have 1 plus the natural log of 1, and then plus x over x, which is also 1. Natural log of 1 here is equal to 0. So this is all 1 over 1 plus 0 plus 1, or in other words, 1/2. And that is the result. That is the limit. Holy cow. That's a tricky problem. Because what did we have to do? We had to identify it as infinity minus infinity, therefore indeterminate. we had to combine into one fraction to put it into a 0 over 0 format. Then we applied L'Hopital's rule, but it was still indeterminate. We did a little simplification, but it was still indeterminate. So we applied L'Hopital's rule again, and then finally it was something that we could evaluate by direct substitution. So sometimes the road is long.